All right, so if I'm going to ask for the chemical properties of HCl, I'm not going to probably come up with a long list of individual reactions here. You know, what does HCl react with? It would be an extremely long list, I think. And so we'll figure it out by, sorry, name again? Chase. Chase. And so what we're going to do is we're going to divide it into types of reactions. So looking at HCl, what are the types of reactions HCl undergoes? And it depends on how you want to classify the types of reactions. You may have learned about like combination. Does HCl undergo combination reactions, decomposition reactions, precipitation, acid base neutralization, double replacement, single replacement? Those, combustion. Well, what we're going to do is we're just going to take all those reactions and then just recategorize them as what were the types of reactions that we came up with, or that I came up with. Well, just three. And what were those three types of reactions that we should consider? Redox, or just acid base with both Bronsted and Lewis, and metathesis. Probably the one I'd like to do first is metathesis, because in certain respects, it's maybe the one you're most familiar with double replacement reactions and this sort of stuff. And so the way I'm going to do this is I'm not going to do like an AB and then figure out all the CDs it reacts with. The AB would be HCl and the CDs would be anything else. Instead, what we're going to do is we're going to look at it based on ion combinations. Metathesis, when we swap the ions, we're looking for favorable or more favorable ion combinations than what you had before. And so the whole AB plus CD swap, I was just saying it favors the other ions more than the existing ions. And so for metathesis, we look at the cation here. And so this is our cation. And then what anions does this cation like? So when we look at this cation, well, one thing we recognize is this is an acid. An acid is defined as H+. So as far as H+ goes, what types of things will H+ react with? And so we saw this yesterday looking at the acid chart here. And so I have a hydronium here. And when I have hydronium and H+, I think of them as interchangeably. You know, it's more correct to express it in terms of hydronium because H+ is just a single proton. You know, if you have a hydrogen atom and you lose the electron, then you're just left with a proton. And a single proton is extremely unstable. It's extremely unstable because of its size. You know, compared to an atom, how big is the nucleus? Do you know how many times smaller the nucleus is? How many orders of magnitude smaller it is than the atom itself? So let's say the atom were this big, how big would the nucleus be? Just roughly, how big? Like half as big? 10 times smaller? 100 times smaller? 1,000 times smaller? 10,000 times smaller? 10 million? Okay, 10 million is maybe a little on the Small side. It's more like 10,000, 5 orders of magnitude smaller. So it's about 10,000 times smaller. And what that does is it means that you have all that charge. Well, it's not all that much. It's +1. But the big difference here is rather than that +1 being spread out over a big atom, that +1 is concentrated in a tiny nucleus. And that makes it extremely reactive, electrically. And so protons aren't stable. They want to react, and they'll react with water immediately to form hydronium. But writing out hydronium is a bit of a hassle, and then you got to balance waters. And so if I don't have to use hydronium, I don't. I just use H+. It depends on the instructor. Some instructors will like to be more accurate, in their equations and will write hydronium. We're going to have cases where we will have to write hydronium. When we do hydrolysis reactions, for example, they all yield hydronium for acids. But for us, we'll just use H+ in place of hydronium here. And so we were looking at this chart the other day. So for example, if I take my acid, which is H+ or hydronium, will chloride neutralize my acid? That is, I want to react my acid, hydronium or H+, with chloride, which is a base. Right? And if that happens, then what's going to happen is H+ combines with chloride over here to form HCl. Do you see the Z pattern here? The Z pattern is chloride will combine with H+ to form HCl. Is that favorable? Are we going downhill in terms of energy? And so we're starting off with this acid here, and we're ending up with this acid up here. Is that favorable? No, that's uphill. This is unfavorable. So we do not expect H+ to react with chloride here. Okay, the same thing can be said, because if H+ did react with chloride, then it's going to form these conjugate bases, which would be H2O, and we're going to lose chloride. And so what we're going to do is we're going to start with chloride and then go to H2O. Well, it turns out that H2O is a stronger base because the bases are upside down. And as we go down on the bases, we go up in terms of energy. And so this is also unfavorable. So this is an uphill reaction. So if we draw a Z here, we'd see, we're going to react the diagonal, and the products are going to be at the end of the Z. However, let's take hydronium or H+ and react it with trichloroacetic acid here. If I take my H+ here and react it with trichloroacetic acid here, is that favorable? And so here, I'm going to take my hydronium, and this is going to be a backward Z here. So we go hydronium, reacts with trichloroacetic acid, donates its proton to form trichloroacetic, or this is called, actually this is not trichloroacetic acid, that's trichloroacetate, sorry. So if I take my hydronium reacted with trichloroacetate, that's going to form trichloroacetic acid. Is this downhill? Yes, this would be downhill because we're starting here at H+ and going to trichloroacetic acid, which is weaker. And so this would be favorable. And so you can see that it just goes downhill from here. Sulfate would be even better because that would be further downhill, right? And the further the downhill we go, the more favorable that reaction is because we'd like to go downhill in terms of energy. In fact, we'd like to go as stable as we can get. Does that make sense? Like a ball rolling down the hill. Well, anyway, this is what we have here. And so what we can say is this. If we're looking at ion combinations, a lot of these bases are ions. For example, trichloroacetate is an ion. Below that is sulfate. Below that is dihydrogen phosphate. Below that is a complex ion, which we'll talk about a little bit today. But below that is nitrite. And so we have a lot of ions. So we can see a lot of favorable ion combinations. And these favorable ion combinations can either be classified as metathesis or acid-base. These are just acid-base reactions, but it's acid-base reactions involving ions. And so when we go back here and we look at the metathesis reactions or potential metathesis reactions for this, although not all these are ions. Do we have any that are not ions? Only ammonia. But ammonia, as you recall, ammonia can participate in metathesis reactions because ammonia does something called hydrolysis, and it weakly hydrolyzes water to form ammonium and hydroxide. You guys remember that? And so ammonia is a little bit weird in that it's not an ion, but can participate in metathesis reactions. So let me go back to that here. And let me drop down here because I'm going to do 3. So we're going to do, if we want to be complete about this, we only need to look at 3. We don't need to look at a whole bunch. So we're going to first consider metathesis. Then we're going to look at acid-base. Okay. And then we'll look at redox, or oxidation reduction reaction. And so if I want to understand the chemical properties of HCl, then I just need to map out the metathesis reactions, the acid-base, and the redox reactions that HCl undergoes. Well, getting back to metathesis, there was only ammonia that was not an ion. So let me talk about that here. Yes. We'll go down a page here. It's not just ammonia. I say ammonia can participate in metathesis reactions, but there are a whole bunch of compounds that look like ammonia, and we call those compounds amines. And so this is ammonia and the amines. Amines are ammonia-like molecules. So if we look at ammonia, and let's throw in a water here. We can have either Bronsted or Lewis acid-base reaction. I mean, they both look the same. And so we can do this as like a Lewis acid-base reaction here, in which the lone pair on ammonia. You recall what was the hybridization of this nitrogen? Is that sp, sp2, sp3? This is sp3. So I have a sp3 lone pair gets pushed into this. You look at this bond here. What kind of bond was that? That's a hydrogen S overlapping. Now this is valence bond theory. Valence bond theory is the overlap of atomic orbitals. So when I think about this bond here, I'm thinking it's an S. And what's the hybridization on this oxygen? Is that an sp, sp2, sp3? sp3 as well. So this is an s-sp3 sigma bond. So this sp3 orbital gets pushed in here and it's going to kick out the other sp3 orbitals along with its electrons. Those get kicked out over here. So when that happens, we form this. We form nitrogen with 4 hydrogens attached to it. Like this. What's the formal charge on this nitrogen? +1. Actually, the formal charge is +1. And we call this ammonium. And so this is ammonia aqueous. Ammonia is pretty soluble in water. It can hydrogen bond to water or react with water. Here, it's reacting with water. To form ammonium. This is tetrahedral. It's sp3 hybridized. So these are all s-sp3 sigma bonds in valence bond theory. And what's the other product? Hydroxide. So the other product is we're going to have pairs go to this. And what's the formal charge on the oxygen in hydroxide? -1. You just write negative. Okay. Ammonium plus hydroxide. Now, in terms of driving force, our driving force is going from stronger to weaker. We want to go from stronger acid to weaker acid, and stronger base to weaker base. Okay, ammonia is our base in the forward direction. Our acid is water, which is donating proton. Or, you can think of this in terms of electron pair or proton. This works both in Bronsted and Lewis. How about if we go backwards? If we go backwards, which one is the base, which one's the acid? Going backwards. It's probably easier to think in terms of Bronsted, because Bronsted, you just look who loses the hydrogen, who gains the hydrogen atom. So going backwards, which one lost the hydrogen? That's our acid. Ammonium. So that'll be our acid. And who gained the hydrogen? Hydroxide. If we go backwards, because ammonium going backwards forms ammonia, 3 hydrogens. And hydroxide going backwards forms water. Backwards. Then we look, which one is a stronger base? Ammonia or hydroxide? Well, ammonia is what we call a weak base. Hydroxide is one of the strong bases. So is this favorable? No, there's no driving force. The driving force is reversed, right? There's no driving force here. And the acids follow. It's going to be weaker acid to stronger acid. And so this is why we say ammonium hydroxide, ammonium ions and hydroxide ions spontaneously decompose into ammonia and water. However, in Chem 1B, we look at something called a dynamic equilibrium. This is downhill in the reverse direction. It's uphill in the forward direction. And so it depends on the hill. So ammonia and water are at the bottom of the hill. This is the most stable. And then at the top of this hill, we have ammonium and hydroxide at the top. Now, the situation is nobody wants to go uphill. Let's say you're on a bike ride. Do you like climbing? Well, some people might like climbing hills, but I don't. I try to avoid that. But if you're in a big group of bike riders, is everybody the same? No, there might be some people who want to climb up the hill, right, as a challenge, correct? And so it turns out that we have the Maxwell-Boltzmann distribution. You guys remember the Maxwell-Boltzmann distribution? What the Maxwell-Boltzmann distribution tells me is that not all molecules are the same. Not all species are the same at room temperature. And so can somebody remind me what the Maxwell-Boltzmann distribution? Maxwell with 1 L and 2 L's. I bet 2. The Maxwell-Boltzmann distribution is important here because the Maxwell-Boltzmann distribution tells us that at 25 degrees C, not everybody's the same. So if ammonia is at 25 degrees C, this is aqueous ammonia, and we have a whole bunch of ammonia molecules in water, do they all behave identically? They're like clones? They're all moving in unison? No. This goes for water molecules, this goes for gas. In fact, they don't all behave. In fact, they're going to have a distribution. They're going to have different energies. And so if we look at the population, some will have low energy. So the low energy ones will hang out at the base. The bulk will have some energy here. And then there's going to be a small tail of high energy molecules. And so let's look at this high tail. This high tail here, these ones are going to have enough energy to climb the hill and make it here. Now, what percentage is that? Well, it turns out this is going to be like 99.9% of the population, greater than 99.9%. And this high energy tail is going to be less than 0.1%. So when I look at this, if I have aqueous ammonia, it's 99.9+% ammonia molecules in water. But there's going to be a tiny fraction of less than 0.1% of these ions here. And so some of these molecules are energetic enough to make it up here. Others will try to make it up, but fall back down. Try to make it up, but fall back down. They don't quite have enough energy to make it all the way up this hill here. Now, the molecules that make it up to the top of the hill, they don't stay there forever because ammonium is a stronger base, and hydroxide is a stronger base than what's down here, so they're going to fall back down. And so as these fall back down, then does this population go to zero? No, the population does not go to zero. The population stays the same. Why? So if some of these ions fall back down the hill to make these molecules here, shouldn't the population decrease? And it turns out it doesn't. You know why? Because you can't stop the molecular motion. You know, at 25 degrees C, there's always going to be a small population here that's going to have enough energy to come up. So if some of these fall back down, then more will go back up. And eventually you'll reach this state of what we call dynamic equilibrium. In a dynamic equilibrium, the rate of molecules going up is equal to the rate falling back down. And therefore, we have this dynamic equilibrium. Now, the dynamic equilibrium here is going to be favored towards the reactants, but the rate going up is equal to the rate going down, but it's heavily biased towards reactants here. Now, you might think less than 0.1%, we typically can ignore that, right? But for metathesis, it doesn't take much to precipitate some things. Like, for example, hydroxides. Metal hydroxides, a lot of them are so insoluble that just a tiny bit of hydroxide is enough to precipitate. And so that's all we need. And so aqueous ammonia, even though it's a molecule, can participate in metathesis reactions. And so what we can say up here is that this H plus reacts with all basic ions stronger than water. Yes, water. But, you know, it includes aqueous ammonia because we have to factor this in. Okay, and so what we call this is, going back to this aqueous ammonia, we call this weak bases weakly hydrolyzed ionized. Weak bases are weak electrolytes. And weak electrolytes weakly hydrolyzed. They weakly hydrolyze. We don't really say ionized for bases because when we say ionized, it splits up into ions. And so if I said ammonia is a weak base, what ions does ammonia split up into? It doesn't. Instead, this would be ionized. Instead, ammonia hydrolyzes into ammonium and hydroxide. But since it's a weak base, it's going to be heavily favored in the reverse direction here. And so ammonia can participate in metathesis reactions, but we typically don't write ammonium hydroxide. We typically just leave it as ammonia because if you're going to go buy some of this, you're going to buy aqueous ammonia. We'll talk more about that later. Let's look at amines next. What amines are they're ammonia-like. And so let's take a look at an amine here, where R is equal to hydrogen or carbon. Now, the carbon is usually a hydrocarbon, typically. And so let's take a look at an amine, a simple amine here. In which I'm going to put 3 of these CH3 groups on here. CH3 groups are called methyl groups. And so this amine is called trimethyl amine. Trimethyl amine for having 3 methyl groups on there. Now, let's compare that to ammonia. Ammonia has a pretty good base. It's not as good as hydroxide. One of the reasons it's not as good as hydroxide is because it doesn't have a full negative charge. If nitrogen had a full negative charge, it would be a much better base. Instead, this nitrogen only has a partial negative charge. This nitrogen has a partial negative charge because of the polar bonds. Nitrogen versus hydrogen, nitrogen is more electronegative. Since nitrogen is more electronegative, it's going to pull more of the electron cloud towards it. And that's going to give a partial positive charge on the hydrogen, a partial negative charge on the nitrogen. And it's got a lone pair. That lone pair means it's able to share. And so when we're looking for a good base, we want as much negative charge and a lone pair, as much negative charge as possible. When we look for negative charge, we either look at bond polarities like this, or we look at formal charge, like in hydroxide, it has a full -1 formal charge. Or we look at oxidation state. Can you tell me what the oxidation state on nitrogen here is? Have you done oxidation state on Lewis structures? When we do oxidation state, we make the opposite assumption of formal charge. Formal charge assumes 100% covalent bonding. Oxidation state assumes what? 100% ionic. If it's 100% ionic, that means winner takes all the electrons. So nitrogen versus hydrogen, which one's more electronegative? Nitrogen, winner takes all. So nitrogen is going to take all the electrons. If nitrogen takes all the electrons, how many electrons does it end up with? 8. So nitrogen ends up with 8. How many valence electrons does nitrogen normally have? 5. So that means it has 3 extra electrons. If it has 3 extra electrons, it has 3 extra negative charges, which gives it an oxidation state of -3. That means hydrogen ends up with no electrons. It's supposed to have 1. So each of these hydrogens is +1. And so that shows this nitrogen's electron rich. To be a good electron pair donor, it should be electron rich. Right? The delta minus shows it's electron rich. The oxidation state shows it's electron rich. The formal charge doesn't show anything because the formal charge is 0. Let's go over here. Which is more electronegative, nitrogen or carbon? Nitrogen. Now, when we compare trimethylamine with ammonia, what's the electronegativity difference between hydrogen and carbon? Is there a big electronegativity difference between hydrogen and carbon, or a small electronegativity difference? In other words, is hydrogen and carbon similar in terms of electronegativity or vastly different in terms of electronegativity? They're very similar. In fact, hydrocarbons are characterized as having nonpolar bonds. All hydrocarbons being carbon-hydrogen compounds, are nonpolar. They're nonpolar because the electronegativity of hydrogen and carbon is very similar. And so this carbon-hydrogen bond is classified as nonpolar. However, this carbon-nitrogen bond would be polar, but carbon is just slightly more electronegative. It's a 2.5 versus hydrogen's 2.1. So what that means is that carbon is going to put up more of a struggle, and therefore nitrogen's not going to get it. So based on electronegativities, we expect nitrogen to have a slightly smaller delta minus. It has just a slightly smaller delta minus because of the slightly bigger electronegativity of carbon versus hydrogen. However, there's a difference. There's one other difference here. What's the oxidation state of hydrogen in ammonia? It's the green number here. The oxidation state of hydrogen in ammonia is +1. +1. And so there's one other difference here we can see. Let's see. Maybe audio is going to be a bit higher now. And that is this. To the nitrogen, we have electronegativity. That's one factor we got to consider, 2.1 versus 2.5. The other factor we got to consider is the electron richness of carbon versus electron richness of hydrogen here. And so what we're going to do is we're going to figure out the oxidation state of this carbon here. So carbon versus nitrogen, who wins? Nitrogen wins, so it doesn't get any of those. Carbon versus hydrogen, who wins? Carbon. So how many electrons does carbon end up with? 2, 4, 6. Carbon ends up with 6 electrons here in the green. How many valence electrons does carbon normally have? 4. So it ends up with 2 extra electrons, which is going to give it a -2 oxidation state. Do you know the oxidation state range of carbon? +4, -4. +4, -4. How did you figure that out? Well, we do it. This is going to be based on total electrons. We do it. Where are the nearest noble gases? The nearest noble gas is neon. Neon has 10 total electrons. Carbon has 6 total electrons, of which 4 valence. And the next nearest noble gas is helium. Helium has 2 total electrons. So if carbon wants to be like neon, how many extra electrons does it have to gain? It has to gain +4 electrons. +4 electrons is -4 charge. If carbon wants to be like helium, then it's going to lose 4 electrons. So if we lose 4 electrons, then it's going to be +4 in terms of charge. And so this is the oxidation state range. The oxidation state range is going from one nearest noble gas to the other. And so let's do the same thing for nitrogen. Tell me what the nearest noble gases to nitrogen are. It's going to be the same, neon and helium. For nitrogen to go to neon, neon has 10 electrons. How many total electrons does nitrogen have? It has 5 valence electrons, but 7 total electrons. That includes core and valence. So nitrogen is going to want to gain how many? 3. Plus 3. Plus 3 electrons means it's going to be minus 3 at one limit. And then to go from 7 to 2, it's got to lose how many? 5. And so if it loses 5, it's going to go plus 5. So nitrogen ranges from plus 5 to minus 3. Carbon ranges from plus 4 to minus 4. So if carbon ranges from plus 4 to minus 4, minus 2 is on the rich side or the poor side for electrons? Minus 4 would be very rich. And so this is electron rich. So on the one hand, carbon's more electronegative. On the other hand, this carbon's pretty electron rich. And so what that means is that the delta minus is probably comparable. And so in terms of base strength, trimethylamine and ammonia are about the same. And the edge would probably go to trimethylamine because it's got these 3 electron-rich methyl groups attached to it. Does that make sense? So I'd expect trimethylamine to be better than ammonia, just slightly. I mean, they're pretty comparable. And so we have a whole bunch of these. So trimethylamine can hydrolyze water to form a little bit of trimethylammonium ion and hydroxide. And so a trimethylamine solution will react in metathesis reactions as well. And it produces hydroxide, which can produce a lot of different precipitates. So those are the amines. There are a whole bunch. The amines don't have to be symmetric like this. So for example, I put in 3 methyls, but they could be mixed up. So for example, this first one could be a methyl. The second one need not be a methyl. And so to show this, I'll put R prime, R double prime, R triple prime, meaning the R's don't have to be the same. They can be the same, but they don't have to be the same. I could have 3 different. So for example, I could put 1 methyl, 2. For the second one, I could put an ethyl, and then the third one, I could put a propyl. You know? Methyl's 1 carbon, hydrocarbon substituent, ethyl's 2, propyl's 3. So let's go back to this here. So when I say ions here, it could be ammonia or the amines as well that would react with this. But we know this is an acid, and since this is an acid, I don't have to take care of it here. There's some overlap here. And so we have acid base here. We're going to be looking at it again. The other ion present is the anion, which is chloride. So what cations does chloride like? Because metathesis are ion combinations. So if I'm thinking about what cations this likes, then the cation either has to form a precipitate, a precipitate, a gas, or weaker acid. Well, chloride's not an acid, so skip that. And so think of a cation that reacts with chloride to form a precipitate. Do you know any cations? Well, we should. Chlorides, bromides, and iodides are all soluble except which ones? Silver, lead, and mercury. So chloride chemically will react with silver ions to form silver chloride, solid. Lead ions to form PbCl2 solid, or mercury 1 ions, Hg2, 2 plus, to form mercury 1 chloride, Hg2Cl2 solid. Are there any other precipitates? No, it's just silver, lead, and mercury. No gas, no stronger acid to weaker acid. So this is it for metathesis. Okay, so let's go on to acid base. H plus is acid. Now, H plus is kind of like the definition of acid. How do you recognize a Bronsted acid? You look for H. But it's not just like, it's not just any H, right? When we think about acid, it has to be what we call an acidic hydrogen. And there's certain ways we write acidic hydrogens. So let me talk about that down here. So for example, CH4, are those acidic hydrogens? No, those aren't acidic hydrogens. Why not? These aren't. We got to think, why not? Um, um, Acetic acid. How do you write acetic acid? Let me ask you this. Do you write acetic acid like this, C2H4O2? I don't know how many people write acetic acid like that. Why do you write acetic acid like that? Anybody write acetic acid like this? Some people do. Maybe they Googled it or something. No, we don't. There could be things called isomers. Have you heard of isomers? Same structure. I mean, not same structure, different structure, but same formula. Normally, we write acetic acid like this. We split apart the hydrogen. And so one hydrogen goes here, three go here. HCH3O, C2H3O2. Sorry, HC2H3O2. This is acetic acid. Why do we do that? We do that because the two hydrogens aren't the same. This hydrogen is acidic. How about these three hydrogens? These three hydrogens are not acidic. These four hydrogens are not acidic. What's the difference? What's the difference is this hydrogen here is more H plus like. These hydrogens aren't. We could see that in an electrostatic potential map of acetic acid. Let's take a look at the potential map for acetic acid. Do you guys remember the color code? Red is positive or negative? Negative, and blue is positive. And so the more positive it is, the better, the more acidic it is, right? So let's say you're a base, you're hydroxide. If you're hydroxide, what do you want? You want your red. And so if you're hydroxide, you're, actually, I maybe I should do this in red. Not blue. If you're hydroxide, you're going to be attracted to the blue regions. So which one do you think you're going to be more attracted to? Sulfuric acid, this hydrogen here. Are you going to be more attracted to this hydrogen here, which is blue, or this hydrogen here, which is blue? Which one? Sulfuric. And the reason why this one's much more blue is it's got a much bigger positive charge. This one has a much smaller positive charge. In other words, this one's quite a bit more polar. And if you're hydroxide, you're going to get a better grip on this hydrogen than on this hydrogen over here. Because what constitutes that grip is a Coulombic attraction. That is, you have to pull the hydrogen off. If you're the base, you have to pull the hydrogen off. And you need to grip onto the hydrogen. And the way you're going to grip onto it is by its positive charge. And the more positively it's charged, the stronger the grip. Let's take a look at the other hydrogens over here. If we look at the other hydrogens, what color is this hydrogen over here? It looks to be neutral, green. If it's green, are you going to get a good grip on it? No. And so these are non-acidic here. You know, the only thing you want to have is a violent collision. If you have a violent collision, you might be able to knock off that hydrogen, but you aren't going to be able to grab it because there's nothing to grab onto. It has no positive charge. Does that make sense for that? And so in acetic acid, we have three non-acidic hydrogens, here, here, and then on the other side, back here. Those are all green. And then we have one acidic hydrogen over here, which is bonded to an oxygen. This oxygen is red. And then we have this terminal oxygen, which is red here. So this oxygen, here. Whereas in sulfuric acid, we have this very acidic hydrogen over here. How about methane? What color would you give these hydrogens here? Red, blue, or green? Green. These would all be green. These would be green here. And this would be red. Or actually blue this side. This would be blue. So if you're a base, you're going to attack that blue hydrogen here, not the greens. So H plus is acid. Does this acid react with all bases in the universe? It's a strong acid. These strong acids react with all the bases in the universe. No. Which bases do strong acids react with? So it's strong acids. Those didn't strong acids react with all bases in the universe? For example, nitrate. Will H plus react with nitrate? No. Why? That's uphill. That's not favorable. And so what bases will H plus react with? They'll react with anything stronger than what? They'll react with all bases stronger than water. With water, it'll be a tie. So if we're looking at the proton here, it's going to be a proton fight between two waters. One water already has a proton. The other one's going to try to take it away. And so it's going to react with all bases stronger than water, which is all these, which we just already talked about, including ammonia. We've already talked about these. One thing about metathesis is ion combinations, but in the gas phase, you don't have to have ions. So for example, ammonia can be a base in the gas phase. Let me just do one more side reaction here before I leave it. Ammonia doesn't have to hydrolyze that like this. And so ammonia could stay as a gas and react with HCl gas. And when this reaction goes, it forms ammonium chloride solid. So it produces a smoke of tiny crystals of ammonium chloride. This is just a straight reaction. There's no hydrolysis involved here. We don't have to form ammonium hydroxide to get this to react. In fact, there's no water. So it can react. Whereas metathesis, we need some ions, we need some water for that. And so there's just some subtle differences between metathesis and this. But what we're going to say for H plus is it reacts with all acids stronger than, not acid, sorry, it is an acid. It's going to react with all, what? Bases. That's what I meant to say. reacts with all bases stronger than what? Water. We can come up with a list. For example, trichloroacetate, nitrite, etc. And so these are pretty much the same. So if you get H plus in metathesis, then you can just say it's an acid. Go to the next step, and just look at the anion here. All right, then the other species is chloride. And what is chloride? Chloride is a base. What acids does chloride react with? Here, so chloride is a base. What acids does chloride react with? All acids stronger than HCl? That would be downhill, wouldn't it? Oh, no, it wouldn't. Would it? All acids stronger than HCl. Yeah, that would work. No. In fact, you should have memorized that chloride is terrible base. Chloride's going to be neutral. Too weak to react.
Super acids, right?
I'm sorry?
Super acids.
Yeah, it could react with superacids, but exotic reactions will consider case by case like that. Too weak to react in water. Superacids, you have to use a different solvent, otherwise the superacid will attack the water. So we don't really consider this a base. So let me put a little asterisk here. Chloride we really don't consider, even though it is on the base side of the chart. It's NR, basically. NR. So we're going to go to H plus in redox. H plus, is it on the left side of the chart or the right side of the chart? Left side or right side? Which one? Left side. Left side is the oxidizers or reducers? Left side is the oxidizers. So H plus is an oxidizer. It's an oxidizing agent. And will it oxidize everything in the universe? No. What is it going to oxidize? Not everything in the universe. So we do the zigzag thing again with the H plus. So one thing I can ask is, will H plus oxidize, let's say, copper? So I'm going to take H plus and oxidize copper. So I go to this zig, like this. And then when that happens, copper gets oxidized to copper 2 plus. So we're going from H plus to copper 2 plus. Is that uphill or downhill? That's uphill. It's not going to happen. We need to go downhill. So if we go H plus, will H plus oxidize lead? Yes. Because if H plus oxidizes lead, then lead gets converted into lead 2 plus. That's downhill because we're going from H plus to lead 2 plus. So that's downhill. That's favorable. Will H plus oxidize H2? No, we're going to get a tug of war for electrons, and it's going to result in a tie. Correct. And so it won't oxidize everything in the universe. H plus will only oxidize the reducing agents on the right that are stronger or weaker than hydrogen. So is lead stronger or weaker than hydrogen?
Oh, wait, no.
It's on the right side. So we got it flipped. It's stronger. And so what I'm going to say here is, because this is not a comprehensive table, all I'm going to say is this. This is an oxidizer, will react with all reducing agents, RAs, stronger than hydrogen. And that includes lead, iron, zinc, etc. Okay, the reason why I'm doing this is, one, we can't come up with a comprehensive list. There are just too many. And so we aren't going to list them one by one. So we're just going to do the criteria here and then look. It's stronger or weaker than hydrogen. Yeah, it's not oxidizing. What is chloride? Is chloride on the left side or the right side of the chart?
Right.
Chloride's on the right side, which means it's a reducer or reducing agent. So chloride's a reducer. Now, will chloride react with anything in the universe? No. We have to look at what chloride will react with. And so let's take a look at what chloride is. Chloride's way up here. So let's take a look. See, will chloride react with bromine? Down here. So this is bromine. So if chloride reacts with bromine, what do we form? Well, chloride reacts with bromine, we're going to form bromide. So we're going from chloride to bromide. Is that uphill or downhill? That is uphill. So that's not favorable. So chloride's not going to react with bromine. So we got to look for something else. Will chloride react with permanganate? Let's go with permanganate and H plus. So if we look at chloride, will it react with permanganate and H plus? Well, if chloride reacts with permanganate and H plus, it's going to form manganese 2 and water. Is that downhill or uphill? That's downhill, so this will react. And so what we're going to say is that chloride is going to react with anything stronger than chlorine. Now, anything stronger than chlorine, well, chlorine is what? An oxidizer or reducer? It's an oxidizer, so this is the way we'll frame this one. We'll just say that we'll react with all oxidizers or oxidizing agents with all oxidizing agents or oxidizers stronger than chlorine. And so permanganate and acid was stronger than chlorine, and so react. So these are the chemical properties of HCl. Most people, when they think of HCl, they just think of strong acid, and that's it. But there's some metathesis properties, and then there's some redox properties as well. So if you take HCl and mix it with permanganate and acid, do you know what you're going to generate? You're going to generate chlorine gas. That's very common. That's one of the chemical properties of HCl. One of the chemical properties of HCl is that you generate chlorine gas by reacting it with potassium permanganate and acid. Very common. So we react the chloride with potassium permanganate and acid. We produce manganese 2 plus in water, and the chloride gets converted into chlorine. And so,
Can't you create oil and gas with bleach
yeah,
and what was it? Was it liquid?
ammonia.
Ammonia,
Yeah, never mix bleach and ammonia. A lot of people think, oh, ammonia is a weak base, no big deal. But ammonia, this is what we're going to look. Ammonia is not on this redox chart. Do you not see it? It's not on this redox chart, nor is bleach. Bleach is not on this one, but it's on a more comprehensive one in Appendix D of our book. Ammonia is still not on that chart. And so this is why we need this. If it's not on the chart, what should we say? Well, there are things that people say. I don't know why I get these pop-ups. One, people say, you never talked about that. That was not in the book. It's not in the book. It's not in the chart, right? It was never in the homework. It's not a fair question. Well, unfortunately, they still throw it at you. Like UCLA was full of unfair questions in that sense because they weren't in the book. They weren't in the homework. And so what you have to do is you have to do a little bit more. You look at the patterns and stuff and then figure it out. We never mix ammonia with bleach. Ammonia and bleach are a bad combination. Ammonia is a weak base, but what are some of the other chemical properties of ammonia? Well, metathesis I talked about. Ammonia can hydrolyze water to generate a little bit of ammonium hydroxide and participate in metathesis reactions. So one, we have acid base, we have metathesis for ammonia, but what about redox for ammonia? Okay, when we get to redox for ammonia, ammonia is not on our redox chart, so what should we do? Well, one, we could assume it's unreactive. Or two, they just didn't have enough space. In this case, they didn't have enough space. Ammonia is very reactive in redox. When we think about redox, the first thing we think is electron-rich or electron-poor. Electron-rich species are reducers. They lose electrons. Electron-poor species are oxidizers. They take electrons. So for example, oxygen. Oxygen is electron-poor because it wants to form oxide. So is ammonia electron-rich or electron-poor? When we look at the formal charge, the formal charge is all zero. Formal charge on nitrogen, 0. Formal charge on hydrogen, 0. So what do we do next? Well, we don't stop with formal charge. Then we look at what? Oxidation state. Now, if you follow the rules for oxidation state in chapter 3, I think it is, you assign hydrogen first. Hydrogen gets assigned first at +1, which means nitrogen will be not -2, close. -3. Is -3 for nitrogen on the rich end or the poor end? It's on the rich end. This is a good reducing agent. Bleach is sodium hypochlorite. We do the same thing. Following the rules in your book, sodium goes first at +1, then oxygen goes next at -2, and that leaves chlorine at what? at +1. So you have a good reducer and you have a good oxidizer. We expect a reaction to occur. This reaction has the potential to form chlorine gas plus other gases. The other gases are oxides of nitrogen. The oxides of nitrogen are all toxic, except maybe nitrous oxide. Nitrous oxide is laughing gas. So people, I don't know how many deaths have been associated with nitrous oxide. Maybe not too many. Nitric oxide is toxic. Nitrogen dioxide is toxic. You know, nitrogen. So we're going to get a reaction. So this is why the rule, safety rule, is never mix bleach with ammonia, ever. Some guy died from this. I think Buffalo Wild Wings, one of the managers there, was a spill. I think it was like ammonia cleaner and some bleach got mixed together, and he was overcome with the fumes and ended up dying. He's a young guy, too. I think it was bleach and ammonia, some kind of cleaner combination. So there are some things that aren't on the chart. But the first thing we do is we try to learn the chart as best as we can. We look for patterns, and then maybe we can recognize some patterns and then maybe make some predictions based on pattern. Because patterns we use all the time to make predictions. We don't need to know the full theory. We can do it based on patterns or laws. All right, any questions on this? No? Okay. All right, so once in a while, we're not going to have a whole bunch of quizzes, but once in a while we'll have a quiz. And today we'll have a quiz, a little quiz. So this will be today's quiz. What are the chemical properties of HNO3? HNO3 is what? Acid. You don't have to tear out a sheet of paper. Nitric acid. What are the chemical properties? And a lot of people say it's exactly the same. Is it exactly the same as hydrochloric acid? Both are strong acids, right? Are they exactly the same? So I'd like you to just do it on this index card here. And this quiz here, this quiz is open book, open notes. And if you get stuck, you can work with other people if you want, or you can work with other people if you prefer, and you can work alone. Pretty informal quiz. I'm going to ask for a hint. Juan? Andrew?
For H plus, you don't have to do it like I did. For metathesis, you can just say H plus C acid section. So you don't have to write it twice. Essentially, it's the same thing.